Hello everyone, welcome to another video. Today we're looking at A2 Physics electric fields, so all that you need to know about electric fields. Let's start off with the basics. What is electrical field strength or electric field strength? All that this is defined as is the force per unit positive charge. So the only reason why we put positive is that we have just defined the electric field to be, by convention, to be coming out of the positive charge. So as you can see here, for a positive charge, the electric field actually comes out of the positive charge and the electric field acts towards the negative charge. So this is just decided by convention as a definition, since we have both positive and negative charges. So we really need to put a common basis on how we define things in physics. So we've just defined it to be force per unit positive charge. So in your exam you really need to remember to write positive to get all of your marks. But writing this as an equation is then just E equals force per charge, and so the SI units would be Newton per Coulomb. Now that we looked at field strength, let's look at what electric fields are. So that is just defined as a region of space where a charged object experiences a force due to its charge. And as we've seen here, depending on whether it's a positive and negative charge, either acts towards or against the charge. So again, this is very just common knowledge, very IGCSE based, and there's nothing really new to look at that. The only new thing here is Coulomb's law. So now what Coulomb's law states is that the force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance. So now all this law does is define this equation. If you watched my gravitational fields video, or if you know about gravitational fields in general, you know that this equation is almost identical to the gravitational fields one. The only difference is our constant k and q1, q2 rather than m1, m2. So this is the force equals k, which is a constant, which equals 9 times 10 to the 9, or sometimes you see k written differently as 1 over 4 pi epsilon, which is the permittivity of free space, which is also a constant. So since we have all constants here, we can sort of just approximate it into one constant k. So that's multiplied by the charge, the charge of one point charge multiplied by the charge of the other point charge divided by the square of their separation. So if we have to visualize this, if we have Q1 here and Q2 here, two charges, this equation is basically defining the force between these two charges depending on the strength of their charges and the distance between the charges, which we labeled as R. So Coulomb's law, all this says is that the force will be proportional to Q1, Q2, since K is a constant, so we can derive it from this equation. And force will be inversely proportional to R squared. So that is a very, very useful relationship that we should remember, and this is one of the bases basically of electric fields and all of the concepts that we've come about defining in electric fields. So when we combine these two equations, the one that we've seen here of electric field strength and the one from Coulomb's law, we get another equation for electric field strength. So all I've done is substitute this F into this F here. Since these two F's are the same, all we get is K Q1 over R squared. So now what we can derive and denote from this is that the electric field strength only depends on one of the charges, and we don't really need both of the charges to be able to calculate the electric field strength. And another important relationship, while I'm at it, I should mention, is E equals the change in potential divided by the change in distance. So you've probably seen this from AS, but if you have a positive plate and a negative plate, then the separation of them, which is the change in D here, which I've written down here. Sorry, it's a little bit messy, but the change in D and the V, which is a change in potential of this. So if this is positive V, negative V, so the difference in the potential divided by the difference in the distance will also give you the electrical field strength. So these are the relationships and the equations that you need to know to sort of define what's happening between charges and between an isolated charge or two charges near each other. So now let's add another layer of knowledge to our basis of electric fields, which is electric potential. So now electric potential is defined as the work done per unit, again, positive charge, which is decided by convention, in bringing a small test charge from infinity to a point. So now if you've seen my gravitational fields video, this is basically the same concept but just defined in terms of electric fields. So if you have a charge Q and you're bringing a small test charge from infinity, so we have infinity as just as a concept to say that it's so far off that we have nothing, basically nothing external acting on this small test charge. So if you bring this to a point near this charge, so if you bring this from here to here, the work done in bringing that would be the electric potential. Another point to note is that the more we move the charge from negative to positive, the more potential energy it has. So since we define this as work done per unit positive charge, so when we bring it from negative to positive, it would have more work done, so it would have more potential energy. If we decided by convention in physics that it was per unit negative charge, then it would have more potential energy going from positive to negative rather than negative to positive. But since we have put a layer, since we have started off with the basis that it's per unit positive charge, then the potential energy would increase if you're going from negative to positive, not vice versa. And another very, very important thing to know, which is written in your syllabus, is that the field strength of a point is equal to the negative potential gradient at that point. So this is very important. It has to be negative. So the negative potential gradient is equal to the field strength at that point. And the reason why this is because conventionally it's coming out of the positive charge, and we saw previously in our positive charge, the field is coming out. So the electric field points out the direction in which the potential energy function is decreasing. If we are looking at the field strength at this point, for example, near this positive charge, then the potential gradient at that point, then this field strength is equal to negative potential gradient at that point, because we are moving away from the positive charge. And since the field is also pointing away, we are not really acting against the field. So the work done that we do is negative because we're going with the field. So work done is basically energy required to oppose a force that is acting on you. But since you're moving with the force, you have to do negative work to reach that point. So that is all that that rule is saying. If you're a little bit confused, you should also check out the gravitational fields video that I made, and maybe comparing those two concepts to grasp this idea a little bit better. So I'm going to put that video in the description as well if you want to check that out. So now let's derive some important equations. So since potential energy is equal to the work done, we can use these two equations. So this is the electric field strength equation. This is the work done equation, which is force times h, or any distance that you move. So if we rearrange this for F and we get QE, then we can sub this F into this F and we get the electric potential energy, or work done, would equal to QEH. this is an important equation that we should remember, which is used often in calculations. And another equation for electric potential energy is VQ, which is potential times charge. So this is also another equation that you should remember. And this is sort of the same concept as gravitational potential energy being the potential times the mass. So all that this is this is electric potential, but instead of mass is the charge. So these two are inherently the same, but we're just applying it in terms of electric fields. And a formula for electric potential, which is again similar to the formula of gravitational potential, except that it's not negative, is that it's V equals KQ over R. So these three equations are something you should really note down and really remember because they're used often in calculations. So now looking into potential, potential is a scalar quantity, whereas field is a vector quantity. So when you're calculating total potential between, for instance, two charges, then you would basically just add the potential of one charge with another charge to find the total potential at the point between them. And since it's scalar, all that matters is the magnitude of the potential. So now moving on to find an equation for the speed of a point charge in a field. So if we have an electric field and we have this point here, so what is the speed of this point due to the electric field provided by this charge? So all that we do is that we equate the kinetic energy with the electrical potential energy, because the electrical potential energy due to this electric field would have to equal the kinetic energy given to this particle or this point due to the laws of conservation of energy. So all that we do is write the formulas, the respective formulas for these. So half mv squared equals qv or vq. So all that I've done now is rearrange for v, and we get v equals 2qv over m, all root. So this is all root, not just the numerator. So this is again an important equation for the velocity of a point charge in a field derived. So now I want to look at cases with two charges and what is basically happening between them in terms of the field and the potential. So when we have two different charges, so one positive, one negative charge, then at the midpoint, the field will not equal to 0. So as we know, the field sort of looks a bit like this. And there's just more and more coming out from each side and going into this charge. So there's no point in this where there is no field at all. So the field will never equal 0 between these two. But at the midpoint, the potential will equal 0 because the potential energy contributed by each charge is the same if the magnitude of the charge is the same, but they're oppositely charged. So if we see the equation of the potential Q over R, this positive Q would be positive Q, and the potential for the negative charge would be negative Q. So if you were finding the total potential and we add these two, then you basically get 0 because you're adding a positive with a negative and they're equal in magnitude. So you get 0 potential at the midpoint, but the field is never 0 between two opposite charges. Now if we look at two of the same charges, sorry, this should be positive here. So if we have two positive charges here, two of the same charges, then the potential can never be 0, but the field can be 0 at the midpoint. So the midpoint here, as you see, the field is basically repelling each other. So obviously there's going to be a little bit that comes off here, and only at the midpoint here is where the vectors would cancel out, and so there would be no field. But the potential will never be 0 because if we look at this equation here, KQ over R, if we find total potential at each point, it can never cancel out because there's no negative charge. They're both positive, so it always adds up to be something, and it never adds up to be 0. One thing you probably think is that the field strength between two opposite charges in the midpoint, if it's non-zero, then it should be double, because if you're adding the vectors of the same magnitude, then you should get double the field in the middle, right? Well, there was a past paper question where this came up, and the answer was basically no, because the charges on the spheres attract each other, and the sphere they're not point charges. So if they were point charges, then the surface of the sphere would not be taken into account. But since they are spheres, then we can't really say that the that the electric pull is the same throughout the whole sphere. So this was something that came up in the past paper, and I thought it was interesting. It's something to add to this explanation. So these 2 points are something you should consider when you're answering questions like those. So looking at the sphere now, so why is the potential in the field not the same outside the sphere as inside the sphere? So that's the reason. So one of the reasons why we introduce the concept of point charges rather than just looking at spheres, because the electric field sort of changes whether you're talking about inside the sphere or outside the sphere. So if we look here, so the graph that we can plot if we're talking about the potential of the sphere, so outside the sphere there would be potential here, but as we go inside the sphere, then the potential is constant, and then when we go out again, then it also decreases. So getting closer to the surface, the potential increases. Then when you go inside the sphere, then the potential stays constant, and when you come out of the sphere, it decreases. So the potential is constant inside the sphere, but the field is zero. So the reason for this is that the electric field is equal to the rate of change of potential. So if the potential is constant, then the rate of change of potential would be zero. Another way to look at this is that if you have a field here, then the vectors would all be pointing towards each other. And when they're pointing towards each other like this, they all cancel out to be zero. So you can either think of it at this way, or you can either think of it in terms of vectors. So those are 2 ways that you can visualize this concept. So now let's look at some graphs of electric fields. If we're looking at single charge graphs where you just have one charge with no other charge or external charge acting towards it, then the field strength of this, as we explained here, will start off to be 0 if we're looking at inside of the sphere. And as we move towards the surface, here, then it shoots up, and the field strength is very, very large on the surface. It's the highest that it can be. And then as you go away from the sphere, then the field strength decreases. And now if we look at the potential here, the potential inside the sphere would be constant. So it's not 0, but it's constant. And as you reach the surface, it's the highest that it can be, which is equal to the constant. And as you go away, it decreases. So that is sort of graphed. This concept is basically graphed here, and that, as I was talking about here, is the same here that is graphed. Now let's look at the graph of 2 charges and what happens between those charges. So if you have A and B charge, where Q is a greater charge than the small q, and if we plot the potential graph, then we see here that the potential is constant, which is the same as the previous graph that we looked at for single charges. But the potential would be greater for the one with the greater charge, because again, the equation that we looked at, if Q is greater, then the potential is also greater. So the potential of the higher charge would be higher than the potential of the smaller charge. So as we're moving from this charge all the way to the smaller charge, the potential decreases until it reaches a point in the center. This is not obviously the midpoint because these 2 charges are not equivalent in magnitude, So this point here, I'm just roughly saying, would be where the potential is the lowest. And then as it goes closer and closer to B, then your point charge or your point object here getting closer to B would now be affected by the field strength of B, and the potential would increase until it reaches the surface of B, and then it becomes constant inside B. So that is sort of how the potential graph is drawn. And if we look at the speed at which this point charge is moving from A to B and what happens to that speed, the basic rule is that the speed depends on the change in potential. So let's start off by looking at the cases. So number one, it increases at a decreasing rate. We're moving closer and closer to this point here in the middle where the change is maximum. The change in potential is maximum. The speed would also be maximum because it's not being affected by the field at B or at A. So the speed increases until it gets to this point where it becomes maximum because it's not being affected by any of the fields. And then it gets closer to B and the speed decreases because it gets closer and closer to the field of B and it gets affected by the field of B. So the speed would decrease and the change of potential would increase then. So that is just a general rule that you should remember. The speed of the particle depends on the change in potential. And also something that that probably helps you visualize is that the electric potential energy gets converted to kinetic energy because of conservation of energy. So whatever kinetic energy is lost by the particle that you were moving from A to B gets converted to the electrical potential energy, hence why the speed depends on the change in potential. So now let's look at the electric field between these two charges. So all that there is that for same charges, which is again Q and Q, big Q and small q, at the surface the electric field is 0. So let's just say A, B. Surface, the electric field in the middle, the electric field is 0. At the surface it's maximum and it goes close. And then, as we talked about earlier, at the midpoint it would be 0 because vectors are pointing opposite ways, so it cancels out, the field cancels out. And as it gets closer and closer to B, the electric field increases again, but in the opposite direction. So since, as we've talked before, since we see here that the field is equating to 0 at a point, then we know that we are talking about the same charges. But if the field was not equal to 0, but the potential graph was equal to 0 at a point, then we know that it's different charges. And this is the same thing. This is what we talked about. In these cases. So all that we're doing is applying that knowledge into how the graphs are made to determine whether or not this graph is telling us if the spheres are same charge or different charges. Now if we look at the graphs for different opposite charged, then let's first look at this electric field graph. If we have charge A and charge B, and they're opposite charges, and let's say they're equivalent in magnitude, that's when we know that the graph will be symmetrical. If they're not, then the graph will kind of be a little bit wobbly like this. But let's just say that they're the same in magnitude. Then at A, the electric field will be the highest on the surface of A. And as you go close, it never becomes 0 since they're opposite charges. But it gets a minimum at the midpoint. And then as you get closer and closer to B, it gets affected by the field at B, and the field strength increases. So this is when we're starting from the positive. And this is for where we're at for the negative, the distance, the x coordinate, basically. So the potential at the surface here would be again the highest that it can be, and then it gets close to the midpoint, it would equal 0 because these are opposite charges, and then as I get close to the minus charge, it becomes negative. So So that is basically all the graphs that you need to know for electric field and all the concepts that you need to know for electric fields. That is this entire chapter wrapped up in this one video. If you have any questions or any clarifications that you need, please do leave a comment down below or email me at my email, which is in the description, so you can have a look at the description for any of the videos that I mentioned in this video. So I hope this video was helpful for you, and I wish you the best of luck for your studies. Bye.